Hello, this is Lab 2 for Calculus 2. The main topic is surfaces of revolution and arc length. This lab is a little bit more involved, so give yourself a little bit more time to work on it. You will be asked to modify subroutines given in this example and even write your own. In our first example, we will talk about a washer method. We will write a subroutine that calculates a volume of a surface of revolution using washer method with Riemann sums. It will also draw a graph of a cross section of the part that we are rotating around x-axis. As a reminder, this is the formula of the washer method. So given two functions f and g, with f being upper function, the volume of a revolution around x-axis is calculated by pi times an integral from a to b, f squared minus g squared dx. So here's the subroutine. It will accept five things, f and g, which are upper and lower functions. These will be a numpy type functions. Then ab, which is our interval. And finally n, which is number of subintervals we will take for the Riemann sum. So the first thing we will do, we will find the volume. We'll find out delta x. Then we will get a list of partitions. Remember here B is not part of this list. So these are in essence left endpoints only, which is enough for the Riemann sum since it does not matter which point we pick. And then finally we calculate our volume. So this is pi and then a sum of difference of squares of f and g times delta x. Now that we have a volume, we will plot. We'll plot both f and g, so we'll create our figure. We get our interval, we plot f, we plot g. Now that we plotted them, we will also want to plot the bar chart that represents our Riemann sums. So this is bar. At xi, this is the height. So this is f minus g, since we are not drawing the bar chart from the x-axis. We want to start at g and go to f. The width is delta x, and this is also a new part here. That's the bottom. This is where the bar chart has to start. Since the g is the lower function, it has to start at g. Alpha is just opacity. It will be blue color, and we are aligning edge to edge. We will also, optionally here, we will plot axis of revolution, which is just the x-axis. So this is the horizontal line, y equals 0. We'll make it gray dashed line. Give it a title, and we will print the volume. So let's see how this works. We will start with x squared as our upper function, g as our lower function, e to the negative x. We will take an interval from 1 to 2, and we will take 10 subintervals. So we define our f, we define our g, we will lambdify both of them, and now we will use washer method. So we have f as upper function, g as lower function, our interval from 1 to 2, and 10 subintervals. And this is what it will look like. So as you can see, we have 10 rectangles here. The blue here is our x squared graph. In orange is our lower function e to the negative x. Then in the gray line, we have our axis of rotation, which is just the x-axis. And finally, on the bottom, we have our volume, which is about 16.99 square units. Now let's repeat the same thing, but taking more subintervals. So in this case, I will take 100 subintervals. As you can see, they will fill up the area between our two graphs very nicely. And we can see that the volume now is 19.05 square units, which is a bit bigger since we have a lot less holes. We can also use integrate to find the volume. So SP integrate, so I have a pi times f squared minus g squared. Notice I'm using here SymPy type functions. The integral will go from 1 to 2. And I will also use n to get a decimal value. So this is, let's call it an actual value of the volume 19.2. So as you can see, we got much closer here. Next, we will look at another subroutine. This one will be quite a bit more complicated. All it will do though is plot 3D picture of our surface. I will try to explain most of the detail of the subroutine. However, you only need to know some of it, just enough to manipulate the code in case you need to change something in it. Inside, small u will represent our interval from A to B. Small v will represent rotation around x-axis. It's in essence will be just a circle. Capital X, Y1, Z1 will represent inner surface that created by function g, and then capital X, Y2, Z2 will create outer surface created by the outer function f. I need 3 coordinates x, y, z here since we are plotting a 3-dimensional picture. We will also use 2 new commands, plot surface, which will plot our surfaces, and plot wireframe, which will plot a grid on top of our surfaces. It will make it a bit easier to see where each surface is. And now let's look at our subroutine. So it will accept 4 things: f, outer function, g, inner functions, and our interval from A to B. We will create our figure. We will use slightly different way of doing it. We will use a subplot routine here because we need to specify that this is a 3D picture. We have our u, which is the interval from A to B. We have our v, which is a circle that will represent rotation. We create a mesh grid of u and v, so this will create all the possible coordinates of u and v. In essence, what this mesh grid created, it created a cylinder that is around x-axis between A and B of radius 1. And what we'll do later, we will manipulate this cylinder, stretching it and squeezing it to create our surfaces of revolution. And this is exactly what this does. It will take our cylinder and will stretch or squeeze by G or stretch and squeeze by F. And so this part creates our outer function and this part creates our inner function. This part will plot a line on a 3D plot, just our axis of revolution. So it will be of length from A to B and it's at 0. The next two will plot our surfaces. So we will plot in red our inner surface and then in blue our outer surface. Then we will plot our wireframes. So same thing, red and blue. These 3 commands limit our coordinates. So in essence, it says on our 3D graph, x will be only between 1 and 2, y's will be between -6 and 6, and z will be between -6 and 6. Finally, this little part is not very relevant. All it will do, it specifies the initial view of our 3D picture. We'll be able to manipulate our picture, but this is what it will show up at first. And then finally show the picture. So let's see how this works. So I'm going to take f and g, same 2 functions, from between 1 and 2. And this is what it looks like. So in blue, we have outer function. You can see the grid. And in red, we have our inner function. It's very small there. And if you look carefully, you see a little black line inside. That's our axis of rotation. As you can see, I can manipulate this graph, and we can also see that our x-axis goes between 1 and 2, and then the other two between -6 and 6. That's what these limits were. Next, let's look at the disk method. There are 2 ways you can do a disk method. One way is to actually write a very similar subroutine to this washer method. It's not very hard to change this subroutine to create a disk method, and this is exactly what you will be asked to do on the exercise problems. You just need to erase a few lines here that deal with second function, so you only have one function. Another method is a bit of a cheat method. In essence, we can reuse washer 3D by making inner function to be just 0. So here's a very quick way of doing this. Since we only need NumPy functions here, I can create a NumPy function right away, and I'm going to use a very quick way of doing this. G equals lambda x is 0. This creates a function. In fact, you can use this method to create any NumPy function very quickly. For example, if I would write something like that, that would mean G is a function x squared. And so let's go back to 0. And now we'll use washer 3D method. So I will use G as my new function here to draw this picture. And as you can see, I can only see really the outer function. You do see the red, but the red is just our axis of revolution now, since it's just a 0 line. Another way we can try to manipulate washer 3D subroutine is by trying to generalize it. What if we want to rotate our graphs around some other axis of rotation? So again, a reminder, this will be the full formula for this. So it's f of x minus c squared minus g of x minus c squared, where c, specifically y equals c, is the axis of rotation. So we will create this new subroutine, washer volume 2, that will accept an extra thing called axis, which will denote axis of rotation. It's very similar to the very first subroutine we had. We still need to calculate our volume using Riemann sums. Notice here inside I'm going to subtract my axis. This is the C in the formula. The plotting of f and g does not change. Plotting of my bar does not change. And plotting of the axis of revolution changes a little bit, since now it's not a 0, it's at the whatever axis is. And that's it. So let's run it and let's try to plot it. So in this case, I want my axis to be at -1. So I'm going to have the same two functions, but now instead of rotating around y equals 0, I will be rotating around y equals -1. And that's the picture. So here's my axis of rotation. As you can see, it's at -1. And the rest is very similar to before. We can redo our 3D picture as well here. So washer 3D2 now, we will add axis. The main change here happens over here and here. So we're adding axis to the y coordinates to move it up. Another change will be here, because now we have a different axis of rotation. It's a different level, not at 0 level. And that's it. That's all the changes we need. So let's plot it. And as you can see, this is our 3D picture. So definitely wider, because now we're rotating around -1. And if you're careful, if you try to see where this black line is, it's basically here at like between 0 and -2, so it's at -1. Now let's look at the second example. In this example, we'll talk a bit more about converting from NumPy to SymPy. Now, up to now, we usually start with the SymPy function and then convert into NumPy using lambdify command. Now, going back, while possible, is quite convoluted. So in essence, we will always use a simpler method, and that's just rerunning a new SymPy function from scratch. Now, normally this type of problem appears when we deal with modeling, because in the modeling, we start with polynomials. and those are a NumPy type of a function. But what if I need to modify this polynomial in such a way that I'll no longer have a polynomial? And that means I have to use some kind of a SymPy type of a function now. So here's an example. Let's say I have x squared plus 1, and I want to find an arc length of this between 1 and 2. So I will create my polynomial using polynomial functions, which is 1 plus x squared. But to find an arc length, I need to take a derivative of this and then take a root of this. I can do derivative using polynomial library, but I cannot do square root. Therefore, I will have to rewrite this function as the SymPy function. So in this case, I have 1 plus x squared. Now this is a SymPy function, and I will integrate it. So it's an integral of square root 1 plus the derivative of fs, which is 1 plus x squared, and the integral is between 1 and 2. So as you can see, it's quite convoluted answer, so I will use n to get a decimal notation for it. That's about 3.16. The last piece in this file is this optional piece of code. It's another way of drawing 3D pictures, in this case using a different library called Plotly. It is quite more complicated, but the pictures I think looks a bit better. This is completely optional. I will never ask you to draw this, but you can use this to play around and see what you can get. So I will import a new library, Plotly, graph objects as go. This is the part that you can manipulate. This is just inner function, outer function, and your interval. The beginning is quite similar to what we had before. I create my cylinder and then actual inner and outer function. This is a new part. I'm using Plotly here to create my two surfaces. Opacity is how see-through it is. Then I will create grid. So I will use longitudinal lines to create a grid. You don't really need to understand this part. You can just copy paste it if you want it. And latitudinal lines. So this is what it will look like. It takes actually a few seconds to plot. Okay, finally done. And as you can see, here's the graph. You can kind of see through a bit. You see our lines and everything. One thing it can also do that the previous library couldn't do is I could zoom in and zoom out as well. Lab 2 will consist of 4 problems. The first problem will be modeling problem. In this problem, you will be asked to modify washer method subroutine to create a new subroutine that uses shell methods. Problem 2 will also be a modeling problem, but in this case, you will need to find arc lengths. In problem 4, you will be asked to modify the washer subroutine to create a subroutine that calculates volume of revolution using disk method. You will be also asked to modify slightly the washer 3D subroutine so that you can draw your surface that has only outer part. And finally, problem 4 will be in essence a combination of things. Here you will have to use washer 3D methods. You will have to find volumes, and you will also have to find surface area. And for the surface area, pay close attention to my note there. You will have to use Riemann sums rather than the integration. And that's it.